All right, good afternoon, everyone. I wanted to
Good afternoon.
by reminding you that Tuesday is our exam 2. I just sent out the review for that right before class. I think it's 19 questions on the review. I do not anticipate the exam will be that long, but that'll give you a good idea of what to expect. There is stuff on the exam that will be covered today. So, make sure that you have done the homework and everything else for today's material before you go and try and do the review. There's a problem from 2.3 that a few students have asked me about. It's number 53. It has to do with a spherical balloon. And it asks you to find the rate of increase of the surface area of this balloon. And they give you the formula for the surface area of a sphere. So if we have a sphere, sorry about that. If we have a sphere that has some radius r, then the surface area, which is, I guess, a measurement of the area of the outside of it, is given by this formula here. And they want to know about the rate of increase in surface area when you change the radius from 1 to 2 to 3. So what this problem is about, it's trying to lead us into some problems we're going to be doing later, some word problems. It's trying to get you to understand that things are not always uniform, in the sense of if you change the radius, obviously the balloon gets bigger, right? And the surface area gets greater, right? So let's say I increase, they're measuring this in feet. Yeah, if I increase, well, if I let's start with this. If I find the surface area with r being 1, so here's radius, here's the surface area. If the radius is 1, right, then I just plug 1 into this formula and I just get 4 pi. So the surface area of a sphere of radius 1 is 4 pi. And in this case, it would be square feet, because when we're measuring areas, our units that we measure in are always squared. If we're measuring the length, it would just be feet. Area would be feet squared. And if it was a volume, it would be feet cubed, right? So at 1 foot radius, the surface area is 4 pi square feet. If I change it to 2 feet, right, increase the radius, the balloon gets bigger, then I plug 2 into this formula and we're going to get 4 pi times 2 squared. And of course, 2 squared is 4, and then 4 times 4 is 16. So we get 16 pi square feet. So when we increase the radius by 1, what happened to the change in the surface area? It went from 4 pi to 16 pi, right? So it changed.
Yeah.
We added how much to it?
12.
12 pi, right? It increased by 12 pi. Understand? The increase was 12.
Yep.
Now, if I go from 2 feet to 3 feet, should we expect an increase of 12 pi again? That's kind of what they want you to see. Will it go up by 12 again? Well, 12 pi, sorry. If we plug in 3, now we have 9 times 4, that's what, 36 pi square feet. And so the increase from here to here was not 12 pi, was it? It was actually 20 pi, right? It went up by 20 pi. So it's not uniform. For every foot that it grows, the surface area is not growing at the same rate each time. If you start out with a really, really big balloon, maybe it's 30, well, no, let's say it's 10 foot wide, and you increase it by a foot, that's going to have a huge impact on the surface area. As opposed to a ball or a balloon that's really small, you increase it by a foot. Yes, you add surface area, but not as much as a bigger balloon increasing by a foot. Does that make sense or not? It's not uniform. So that's all they're asking you to do, is just take a look at what happens at the rate of change as you go from one to the other. Anna Marie, does that kind of get to your question? Yes. This is not a very important. This is not a very important thing for us in this now. It'll become important later, but really what we're going to look at later is trying to measure how fast the surface area is growing at an instant in time, as opposed to over an interval of time. Like here, we're looking between 1 foot to 2 foot or 2 foot to 3 foot. We're going to be talking later about looking at an instant, which is what calculus has been about, right? Finding instantaneous rates of change. Okay.
I was going to say, on the answer key, it has the first one as 8 feet. Is that just a mistake?
It has what?
For A, it has it as 8 feet squared. Is that just a mistake, or?
8 feet.
It has it as feet squared divided by feet.
Yeah, they're looking at a rate of change, right? So they're looking at a rate of change. When you look at a rate of change, it's always going to be, let me do it this way. This might make a little more sense. Remember when we were doing the problem and we had here like time measured in, let's say, hours, and then here we had distance measured in, let's say, miles, and we had a graph, and we talked about the slope of the tangent line, and we said the units on that slope, right, whatever this slope is, the units would be this divided by this, miles divided by hours. So that would be miles per hour, right? When they're talking about a rate of change here, they're talking about, if we graph this, this would be the surface area, this would be the radius. The radius is in feet. The surface area would be in feet squared. So some rate of change would be this unit over this unit. Yes. Now, so I'm not saying that the answer here, this is the answer in the book. That's not what I'm saying. I'm trying to get you to see that it's non-uniform, right? That the jump was 12 and then here it was 20.
No, I get that. Where did they get the 8 from?
From, what did they put? Find the rate of increase with respect to the radius when r is 1, 2. I'd have to look at the answer to see what you're talking about. Give me a minute to bring it up. Chapters is 2. Just bring it here so you can see it. What is 2.3, number 53?
Yeah.
And slow. Yeah. So what they're doing is looking at the instantaneous, right? So they're saying, here's your function, right? And so when you take the derivative of this, what do you get?
Oh, okay, yeah.
R, right? 8 pi r. And they're saying, okay, at 1, the rate of change is 8 pi, here's 16. That's the mechanics of what they want you to do. What I was trying to answer a student's question about the units and how this is not uniform in the sense of the rate of change. At the end of the day, the derivative of this can be found using the rules from section 2.3. Does that make sense? And then you can just evaluate that at the 3 different points. Okay, don't get bogged down with this. This problem is not going to be on the test. It's, it'll come later. We'll have more time to talk about it. I should probably just take it out because it just confuses students more than anything at this point.
I have a quick question.
Okay.
So 2 things actually. One thing is I downloaded the review and I looked at it, and the first fistful of questions say to use the definition of the limit. Does that mean you want us to do it the long way with our x plus h formula?
Mm-hmm.
Is that what that means? Okay.
Yep.
Also on the homework, and then I also saw it on the review. I opened it and just looked at it this morning. there's one of those questions at the bottom that is a sine or it's a cosine, and it's going to take the like 120th derivative. There it is. So there was one of those on the homework. It was doing the 99th derivative of the sine of x.
Mhm.
And I watched your video. I watched your little homework video.
Yeah,
Any of them where I look at it and go, oh, I
Yeah.
watched your video. And I was just going to ask if you could maybe go over that concept a little more, because like I understand it conceptually, but like,
yeah. Let me.
Yeah.
Yes, that's part of what I want to do today. There are a few things from 2-3 that came up in terms of the homework that I hadn't completely talked about, which is I think I warned you that something like that would happen when you get to the homework. Normal lines. Okay, I didn't discuss what a normal line is, and then I also did not show you how to do something like take the 99th derivative of sine, right? Those are two things. So let's address those. That's what I wanted to start class with. Let me do the normal line
Sweet.
first, because that was part of my plan. Let's do normal line first. Then I'll talk about how to take a really high derivative of something, and then we will be done with that, and we can start talking 2.4. All right. So let's look at a graph of something. Let's just kind of go back to, oh, hey, there's your review problem. I'll just start a new one here. Okay, so let's just take a very basic function, x squared. All right, there we go. There's a problem, right? We know, at least I hope we know in this class, how to go to some point on that graph, let's say 2, 4, right? And we would know how to find the equation of that tangent line, right? I hope we would feel comfortable doing that by now. Let me go ahead and graph that equation for you. Yeah, how do I want to do this? I guess I can just do it here. That's fine. There we go. So there is the equation of the tangent line at that point. Everyone agree? It's the equation of the tangent line. Now, a normal line, this is what a normal line looks like. It's easier, I think, if you see it first, and then we can talk about what it is. Forgot my minus sign. There you go. That's the normal line. So the tangent line touches the graph at a single point and runs, right up against it. It's tangent, right? The normal line also goes through that point, but is perpendicular to the tangent line. Okay, so it intersects the tangent line at a right angle. That's called the normal line. Okay, so normal line, tangent line. So you have to go back to college algebra. When you are given a line, and let's say that the slope of the line is some number, then a line perpendicular to that, what's the relationship between the slopes? Like if they're parallel,
Like reciprocals or something?
Yeah, what is it?
Negative versus
Reciprocal.
The negative reciprocal or the opposite reciprocal. So if you're given the slope of a line perpendicular to it will have a slope that is opposite in sign and the reciprocal of the original number. So look at my answers here. When I did this, this is basically me using the formula y minus y1 equals m times x minus x1. So this 4 right here is what I got when I took the derivative of this function and figured out what the derivative's value was at 2, using 2 because 2 is x. When I did that, I got 4 as my answer. Now, I graphed the same line, right? Same y1, same x1, right, as this. The only thing I changed was the slope out front. I took this number, looked at it as 4/1. Then to find the perpendicular, I flipped it over and I changed it from positive to negative. And I made that my slope and graph that line, and then I get the normal line. So what I'm saying to you is that for the problems that ask you for the normal line, all you have to do is first find the equation of the tangent line. And then to write the equation of the normal, just take that slope you had, flip it over and change the sign, and you're done. That makes sense or not? No?
I got it.
I'm seeing nods of yes, so.
That one I was able to basically just go on to Google and find some quick definitions of the normal line.
Normal line, yeah. Okay, so that's normal line. We're going to move on now. I've been asked about this question. I'm actually going to do the one in the homework, even though I have a video for it. Basically, the problem is saying take the 99th derivative. This is the notation we use for the 99th derivative of sine of x. Now, you could just start taking derivatives, right? Take the derivative once, then twice, then 3 times, and you could keep doing this 99 times, but that's not the point of the exercise. So to prove that it's not the point of the exercise, I'm actually going to change it from 99 to 994. That way, I'm going to prevent you from wanting to do it by hand, all right? Unless you want to do it 1,000 times almost, right? So here's the idea. With the sine function, when you start taking its derivative and you start doing derivative after derivative after derivative, you start to see a pattern, okay? So let's start first by listing out the derivatives. So I'm going to make a table. This might make it easier for us to understand. In the left column, I'm going to put the derivative that I'm taking. And then over here, I'm sorry. Yeah, I'll just put the derivative that I'm taking. And then here's what the answer will be. Okay. So let me start filling out this table. Remember, our function is sine. So if I take the first derivative, that's what I mean by 1 here. If I take the first derivative, what is the derivative of sine of x?
Cosine.
Cosine.
Couldn't that be cosine of x?
That's it, just cosine, right? Now, if I take the second derivative of sine, that means I need to take the derivative of the derivative. Well, here's the derivative of sine, right? So take its derivative. So what's the derivative of cosine?
Negative sine.
Negative sine.
Negative sine, right? We have to remember that, right? Now we have to take the derivative again. This would be our third derivative. Now this negative in front, treat it like a constant. So bring it for the ride. And then take the derivative of sine, which we already know is cosine. So now we have negative cosine x, right? Now we take the fourth derivative. The negative in front, again, is like a constant. It can come for the ride. And then the derivative of cosine of x we know is negative sine x. And negative become sine, right? So negative and negative, or minus and negative becomes positive sine. And wait a minute, we're back where we started, aren't we? Because now we're just going to repeat the pattern. It's going to keep repeating that pattern. So I want to add one more thing to this table. Up here, the zeroth derivative. We haven't talked about what the zeroth derivative is. The zeroth derivative is just don't take the derivative, okay? That means it's the original function. Does that make sense to you? The zeroth derivative of a function is the original function. The first derivative is, well, take its derivative, second, third, fourth, and now watch what happens. The fifth derivative, I'm just going to repeat the pattern here. So it should be cosine x. After cosine, I got negative sine. After negative sine, I got negative cosine again. And then after negative cosine, I go back to sine. And then it's going to repeat again, right? So I'm going to have cosine again. I'm going to have negative sine. I'm going to have negative cosine. Then back to sine. And that's just going to continue over and over and over and over, right? Forever. This is the sixth derivative, 7th, 8th, 9th, 10th, 11th, 12th, right? And I could just keep going with this. The question is, what is the 994th derivative? So, I mean, there's a lot of different ways to try and go about this, but I'm going to show you the way that, or try and explain to you the way that I think is most beneficial, especially if you're a computer science major. This is a good thing to know about if you don't already know about it. So let's look at the things let's look at where we have the same answer coming out. So let's see, I have sine here. I've got another sine here, another sine here, and then another sine here. Those are happening when my derivatives are 0, 4, 8, and 12, right? 0, 4, 8, and 12. And then the next one would happen when?
16.
16, right?
Then 20,
So
then 24.
there's a common jump, right? We jump by 4 here, 4 here, 4 here. There's a jump of 4 each time, right? So I should expect that the 16th derivative should also be sine. Also, the 20th derivative should also be sine. Make sense? Let's do the same thing for the next one. Cosine. Cosine happened here, 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 and then it would have happened here. I didn't have it, but those are happening at 1, 5, 9, and then the next one would have been 13, right? Do y'all see that those also jump by 4?
Yeah,
Yes, they jump by 4. So the next one would be 13. What would be the one after 13?
17.
17, right? So I should expect that the 17th derivative of sine should be cosine. Understand? Let's do the next one. There's only 4 possible answers, right? It's either sine, cosine, negative sine, or negative cosine. Those are the only 4 possible answers. Here, this one, this one, this one, and then there would be another one down here. Those are happening at 2, 6, 10, and then the next one would be 14. Again, they jump by 4, don't they? Jump by 4 each time. And then the last one, and let me see if I can get a different highlighter color. I'm kind of limited on my highlighter colors. Let me try this. I don't know what's going to happen. That's not what I want. Okay, try this one. That's not bad. That. Those happen here, here, and here. And again, don't they jump by 4? 3 to 7, 7 to 11. The next one should be what, 15 down there?
Yeah, it should be 15.
So all of these jump by 4 each time. So there's something very special about this number 4. All right, we have 4 possible answers. 4 possible answers. And those are the only possible answers we can get, right? 4 of them. We would say that this derivative is cyclic. Cyclic, meaning that it cycles through, right? It continues a cycle. It goes through a cycle. Sine, cosine, negative cosine. Then it cycles again. Sine, cosine, negative cosine. Continues the cycle. So if you look at, if we know that that there are 4 possible answers, then there's something very kind of unique about these numbers, right? Like all the yellow ones, all the green ones, all the blue ones, all the kind of orangish ones, they all have something in common with one another. And it's kind of elusive until you understand this thing called modular arithmetic. So this is where computer science people will benefit from this if you haven't seen it. So I'm going to write something down here. I'm just going to put mod because that's what we call it, mod. All right, so this is a new operation. If you haven't seen this before, here's how it works. I'm going to give you some number m. Yeah, no, let me keep the variables so you can distinguish. If I say x mod y, if you see me write x mod y down, this is going to give you an answer, okay? This is going to be some answer here. And what that answer is the remainder you get when you divide x by y. It's the remainder you get when you take this number and divide it by this number. I'll give you an example. What is 10 mod 3? So that means you take 10, divide it by 3. 3 doesn't go into 10, right? Not evenly. So I'd have to multiply by 3. That would be a 9 here, and then I'd subtract and I'd get a 1. And that would be my remainder, right? My remainder would be 1, right? So the answer to this is 1. 10 mod 3 is 1. With me?
I haven't seen remainders in a very long time.
Yeah, right. It's like we stop using them, then we start using them again. So here's another one. Let me go 14 mod. What's 14 mod 2?
Would it be nothing?
There's no remainder.
It would be 0.
So 0 would be the answer. Man, I should have stuck with 10 mod 3. Well, you know what? It's okay. Just kind of, we did this one, but let's kind of scratch this out of our heads for a second. Let's
I
do
have a
another number
question.
mod 3. Let's do another number mod 3.
I
How
have a
about,
question.
was there a question? Yes, I'm sorry.
How did we get to 0?
So this 14 mod 2 means you take 14 and divide it by 2. 2 goes into 14 7 times, exactly, right? So you get no remainder. So this is your remainder, right? 0, so your answer is 0.
Okay.
Make sense?
Yeah.
Let's do another mod 3 though. Let's do 11 mod 3. What's 11 mod 3?
2.
2. So take 11 divided by 3. You'll have 2 as a remainder. What's 12 mod 3?
0.
0, right? You only, because if 3 goes into 12 evenly, you have no remainder. Let's do 13 mod 3. What's your answer?
That should be 1 again.
1, right? Because 3 goes into 13 actually 4 times with 1 left over, right? 1. What do you think 14 mod 3 is?
2.
2. What do you think 15 mod 3 is?
0.
What's the remainder? Nothing, right?
Yeah.
Do y'all see something happening here? If we do mod 3, what are the only possible answers that we are getting out?
0, 1, and 2.
0, 1, 2, right? So if you do mod 3, there's only 3 possible answers that can come out. Yes? 0, 1, or 2. So if you think back at, to what we're doing here, what we want is to somehow classify these things. So let's take a look at the list that we have here let's look at the yellow list first of numbers. We had 0, 4, 8, 12. Anything from this list, we know when we take the derivative, the answer is going to be sine x. Do y'all agree? If this is the derivative we're taking, the answer is going to be this. Yes? Okay, think about that 4 again, right? There's 4 possible things in this cycle. So what do all of these have in common? Think mod. Think mod here. If I do these numbers modded with what? They all have something in common.
If they're all modded with 4, they get to 0.
Yeah, if they're modded with 4, let's just grab one of them, 12. What would happen if we do 12 mod 4? Well, 4 goes into 12, right? Evenly. So we get 0. What about 8 mod 4?
0.
We also get 0, don't we? 8 mod 4. Because 4 goes into 8 twice with nothing left over. What about 4 mod 4?
0.
0. Okay, the weird one is this one, 0 mod 4. The answer is 0. Because how many times does 4 go into 0?
0.
As many times as you want, okay, with nothing left over, because all you have to do is multiply 4 by 0 and you get that. So 0 mod anything is 0, okay? So when you mod 4, when you take the number and you mod 4, you get 0. All right, maybe that's a coincidence, maybe that's just interesting, maybe it's the actual thing we need to answer this question. How about the other list? 1, 5, 9, 13. 1, 5, 9, 13. If we take the derivative, we get cosine, don't we? What do all these have in common when you mod 4, when you do a mod 4?
Wouldn't they get you out of 1?
They get you a 1, right?
Mhm.
If you do 5 mod 4, your remainder is 1. If you do 9 mod 4, well, 4 goes into 9 twice with 1 left over. 13 mod 4, 4 goes into 13, what, 3 times with 1 left over?
Yeah.
These are all mod 1s, aren't? I mean, these all modded with 4 give you 1. Yes?
Yeah.
What about the list of the orange numbers here? Try and squeeze this. 3, 7, 11. The next one would have been 15, we do any of those, the answer will be negative cosine x. But what do you get when you mod these? I'll just do 7 mod 4. What's that?
Two?
You should get 2, right?
Yeah.
Is it 2? Hold on.
No, that's 3.
That's 3, isn't it?
Mhm.
Isn't it 3?
Yeah.
It's
Yeah.
3. I think did I skip one? Sine, cosine. Oh, you know what? I skipped the blue one. I'm sorry. That's why we didn't get 2. The blue ones, I forgot to do that list. 2, 6, 10, 14 would be the next one. When we do those derivatives, we get negative sine x. If we do any of these numbers, 6 mod 4, we get 2. And you can check it for any of these. Take any of these and mod it 4, and you're going to get 2. Take any of these, mod it 4, you're going to get 3. Yay or nay?
Yeah, that seems reasonable.
Okay, so if I want the 994th derivative, then I just need to figure out what classification that number falls into when I mod it with 4. Does it spit out a 0, a 1, a 2, or a 3 when I mod it? So take the number 994, divide it by 4, and see what your remainder is. So 4 goes in there twice. It gives me an 800, and then I subtract, I get 194. 4 goes into here, I think, what, 4 times? Gives me 160. That leaves me a 34. 4 goes into there, how many times? Even. I can do 8, I think, right? 8.
8.
And you get 32, and you get a remainder of 2. Right? You get a remainder of 2. So 994 mod 4 is equal to 2. That means it falls into this group right here, which means the
Negative
994th derivative is negative sine x.
Oh, that's really cool.
Is this like what discrete mathematics goes into?
I think they probably do talk about it. Let me see if I can find something. I have something here that might, yeah. Let me see if I can bring this up. I actually used this mod just the other day. Let me see if I can remember how to get in here. So I have a Fitbit watch, and I'm getting old, so my eyes are really bad. So, you know, with a Fitbit watch, you can, which one do I have? I think I have that one. Where's my stuff? Hold on. I'm trying to look for mine. Where are mine, dude? Come on. Oh, there they are. Okay, so I found this app that you can get that you can create your own watch faces, because I was having a problem. I needed mine to be big enough in certain places so I didn't have my glasses on. I could tell like certain things. So I'm going to try and show you all this. I don't know if y'all can see my watch, but can y'all see that? Kind of. All right. I made this watch face. And one of the things that happens is when my battery gets to a certain point, okay, when my battery gets to a certain level, like maybe 10%, I have something come on screen and start flashing, okay? I designed it to do that, but I didn't want it to flash every second. I wanted it to flash like every 3 seconds, because every second was kind of like a pain in the ass. So let me see if I can get into this. Gosh, hold on. There we go. Okay, so I need to see if I can remember how to do this. I haven't been in here in a while. Here it is. Okay, so it's hard to understand this because this is actual code from their little program.
Yeah, what is it language?
I have no idea. I have no
Yeah.
idea what the language is. But this right here, the symbols that are using right there is basically me saying to take the time, whatever time it is, the seconds, look at the seconds and mod it 3. And if you get 0, then this is telling it to flash. And so what that's doing is it's taking, like, let's say the clock is like at 42 seconds. Or let's do an easier number. Let's say the clock, it's 18 seconds into that minute. This will go and it'll take 18 seconds. It'll mod it with 3, right? So what's 18 mod 3?
0.
0, right? 18 mod 3 is 0 because it goes in 6 times with no remainder. This is checking if that time at that time mod 3 is 0, flash. Okay. If it's not 0, then don't flash. So anyway, I'm just showing you, like, I've actually used mod like recently to do some custom design on a watch face for a freaking app, which is useless. But computer science people don't use this all the time because a lot of times you're trying to classify numbers into groups. Instead of having just all these numbers, you kind of classify groups of them. And mod is a good way of doing it. Okay, I'm off topic. All right, I hope that helps. Does this help?
Yeah, that's actually really helpful.
Okay.
I have a quick question.
Hold on, before you get to it. I would never
Okay.
have expected you all to get that on your own. Okay, this is a problem I always expect students to ask me about because not many of you know mod. And there are other ways to do it, but no one wants to crank out 99 derivatives, right? There's got to be a more efficient way of doing this. So this is the way. And now that you've seen it, you know that this is something that you could perhaps take on, right? This is on the review for the test. Hunter, what was your question?
Oh, I was just going to ask, is there any way to do mod on a calculator besides divide and then multiply?
I think on most graphing calculators that have some brains to them, yes. On a basic one, I doubt it.
Okay,
But
cool.
on
I was just wondering.
on TIs, I'm pretty sure there's a mod in there.
Neat.
Yeah.
Just wondering, because that seems like something that, man, being able to just plug 12 mod 4 into a calculator would actually be pretty nice. Or 999 mod 4, which is really where it would be more nice.
Yeah.
But I mean, even without that, it's not hard math.
Yeah. I mean, it's just arithmetic right here.
Yeah. It's unfortunately the hardest part of math.
Yeah.
I've hit that point where I'm better at algebra than arithmetic. I'll breeze through some big long algebra that you assigned, and then it'll have me adding some numbers at the end, and I sit there and struggle over that.
Yeah, my brain stopped doing arithmetic a long time ago. Most people think like math majors are like these human calculators. That's not the way it works. Okay. All right. I think we're ready to move on to the next section. All right. So just as a recap, I mean, we should all understand these formulas from before. Derivative of a constant is 0. Derivative of x is 1. Power rule, the very important power rule. If we have a constant attached to the function, it comes for the ride. If we have addition or subtraction between things, we can do them individually. And then the trig stuff, we should know derivative of sine is cosine, cosine is negative sine, tangent, secant squared. And then the other 3 I said, just remember they're on your formula sheet, right? And that's kind of where we are. That's it. And we're struggling with this idea of how to take the derivative of, and this was the problem I ended class with last time with the quiz, right? It was this problem. This one right here. Yeah, this is what I ended with. We had graphed this. Do y'all want to see this again? I can show it to you. I think I have it. I know I have it. It was this one here where we said we have this function, the red one, and we wanted to know what its derivative was, right? So this is the red function right here. And we were talking about how to take its derivative, right? And we said, oh, you have a plus, so you can do these individually. And so the derivative of 2 was 0, and we were happy about that. But the question became, how do you take derivative of this? Because there's multiplication between two things. And so I said, well, maybe life is good and we can take the derivative of each one separately. And then I showed you, if we did that, it doesn't work. We actually get the wrong graph down here as the derivative. Y'all remember me doing that?
Yes.
And then I showed you what the right graph is. So the correct answer here, I believe, was the blue one. Yeah, it's that answer right there. Okay. And I told you, here it is, sine x plus x cosine x. So that is the correct answer. Why is it this? Well, we need the product rule. So here's the rule. All right. Here's the product rule. I'll go back to the notes and show it to you, but the product rule is this. And I'm sad I'm not going to prove it to you, but time is not on our side right now. Okay, so we're just going to have to get the rule. So here's what the rule says. If you have some function y equals some function of x times some other function of x, so you've got a product there between the two, and you want to take the derivative of this, then the answer is this. You will take the derivative of that first function f. Then you will multiply it times g, but you will not take the derivative of g. Then you will add to this. Now you take the derivative of g, but this time you multiply that times f and you don't take the derivative of f. So it's like they're going to take turns, okay? To take the derivative of a product, you first have to take the derivative of the first one, multiply it times the second one, add to that the derivative of the second one times the first one. So it is the derivative of first times the second plus derivative of the second one times the first. That's what it is. Do y'all see that in this? The derivative of the first one times the second plus the derivative of the second one times the first. And that's the formula for it. All right. If you do that, that is the correct derivative. And again, I'm sad I'm
That's
not
pretty
proving it.
nice.
So let's do it. Let's take that. Let's just take that one piece. Let's not take the whole thing. Let's just take that one piece from last class. Just the x sine x. Let's just do that. And I'll come back to this problem. So if I take, for example, I say, let's let y be equal to x sine x. And I ask you to find y prime. All you have to do is, well, you have to first recognize that you have a product. Okay, everyone here needs to see that you've got multiplication right there between those two, right? And so that first thing you have here, that's kind of like the f of x. And the second thing you have here is kind of like the g of x, and they're being multiplied. Just like this. And so now we just go to the formula. I recommend that you memorize this more than you memorize a formula. Memorize the pattern of the formula, because we won't always have f and g. It won't always be f and g. Sometimes it'll be u and v, or h and k, and in calculus it may be some, cal 2 it might be something else. The product rule is an operation that you do. So you take derivative of the first one, multiply by the second, you add to that the derivative of the second one times the first one, and then you're done. So I'm going to do the derivative of the first one. Well, that I can do, right? The derivative of x, I'm happy with. That's what?
I have a question.
One.
Was there a question? Yes?
Can it continue past just two functions? Can you do like 3 or 4, etc., or is it just the one?
Yes, you can. Well, let me, I'll show you how we do that. You're not going to be happy, but I will show you how to do it. Okay. So we take the derivative of the first one. Now, here, let me show you one way that people like to write this sometimes to keep track of what's going on. They say, okay, I've got to take the derivative of the first one times the second one plus, then I have to take the derivative of the second one and then multiply times the first one. Do you see what I've done? I haven't actually taken any derivatives. I've just written down what I need to do. And now I actually do it. The derivative of x is 1 times sine x, and then plus the derivative of sine x, which is cosine x, times x. Now, 1 times sine x is just sine x, so I'm just going to write sine x there. And then this is a little tricky, be careful. You cannot put these x's together. This x is trapped in the cosine, and this x cannot just go join it. So the proper way to write this without there being any confusion is to put the x on the back out to the front. And that way everyone knows it's x times cosine x. And that's it. You're done. What do y'all think?
That's not too bad.
Not too bad.
It's a nice formula.
So if we go back to last class where we had this function now, right? Let's do this one because this will just kind of finish what we were doing last time. If I give you this function, the only difference in the derivative is this. See, this is why I don't like to memorize f, g, because the name of this function is f, isn't it? Like what we're looking at is f. So I need to first see, okay, I can do these separately, right? I can do this one and this one separately because there's addition. So when I take the derivative of this, it's going to be, well, I have to take the derivative of this and then add to it the derivative of that. That's the rule that says if I have addition, I can do them individually. So I haven't done any derivatives, right? This equals, now, how do you take the derivative of this product? We just did this problem, right? There's our product. So on this, it would be the derivative of the x, derivative of the first one, times the second one, plus the derivative of the second one, times the first one. And all that, everything I've written down here in gray is just that product rule on that. I still have next to it plus the derivative of 2, right? What's the derivative?
It should be 0.
It's going to be 0, but I'll put it there anyway. And then my next line, I go ahead and take these derivatives. So 1 times sine x. I'm basically just repeating everything I just did. And I don't need the plus 0. So there it is. That's your derivative.
I have a question.
Yes, Vasily?
So what happens when we multiply x cos x with another x?
What do you mean?
Like, is it gonna be x squared?
This cosine x times x? Is that what you're asking?
No, the one at the bottom.
Oh, no,
Yeah, this one.
no, that is just x times cosine x. That's it. You cannot put this x in here.
Yeah, what if it's multiplied by another x?
Then it would be x squared cosine x.
Oh, okay.
So if you had this, let's just say we have this sitting here, and I say, hey, I want to multiply that times x, then this would become x squared cosine x.
So it'd be on the front, right?
Yes, it would only be if you cannot. This is like a bank vault. Okay, you're not allowed in there. Okay, like it's very difficult to get into the argument of a trig function. You can't push things in there. You can't mess with it. The only way you can manipulate the argument of a trig function is if you're using some identity, some like double angle identity or power reducing identity or something like that. Other than that, the inside of this is like off limits.
Okay, thank you.
Okay, I'm going to do another example. And Maddie, I'm going to get to your question, but I don't think y'all are wanting that question answered yet. Okay, let me do something a little bit nicer, I guess. How about this now? I'm gonna go with y equals x to the 7th tangent x. Find y prime. All right, so you have to recognize the product. Does everyone see the product?
Yes.
Right here. Okay, so I have a first function. This is my first function. This is my second function. See, I'm not really using the f and the g anymore. Just kind of thinking through this. I have a first and a second. The derivative of this should be, according to the product rule, the derivative of the first one. So whatever the first one is, take its derivative, times the second one, do not take the derivative, plus the derivative of the second one, which is the derivative of tangent, times the first one. I have not taken any derivatives. I've just written out the formula. And now I crank it out, right? X to the 7th I can do, right? Derivative of that's what?
7x to the 6th.
7x to the 6th. Power rule from last class, right? Times tangent x. Plus, now I need the derivative of tangent. So I need to remember what we talked about last
That
class.
should be
Secant
the
squared x.
Secant
yeah,
squared
secant
x
squared x times x to the second. 7.
times x to the 7th. There we go. And that is it. I mean, that is the derivative. Now, I like to call this the raw derivative. It's kind of like the derivative that comes out right after you apply the rule. It looks like that. Now, you could do some algebra to this if you wanted. Like there are some things I could do if it would not be necessary, but I could do this. This wouldn't be wrong. I could factor an x to the 6th out because they both have at least an x to the 6th. But you know what I'm gonna do here? See that x times x to the 7th here? Again, those can't go together. This x is trapped in the secant. So I moved the x to the 7th out front, and then I pulled an x to the 6th out, which left one x still there. This step is not necessary. I'm just showing it to you because later on, we will need to do some algebra to this. And so you may as well get used to the idea of simplifying it. On this first test over this though, all I care about is the raw derivative. Just show me you can apply the rule correctly. I'm curious to know if we're satisfied with that result. Let's see, let's do a new graph. The original function was x to the 7th times tangent x, right? That's the graph, that's the function. God, that is nasty. Okay. And then our answer, the derivative, was 7x to the 6th times tangent x plus secant x squared times x to the 7th. It's going to be hard to check this, but I'll just look at it here. The original function is the red one. And it looks like at 0, I have a flat tangent line here on the red one. And that means I should have an x-intercept on its derivative, which I do. Also, the slopes of the tangent lines over here are positive, which means my derivative should be going positive numbers over here, which it is. It's right. I'm not concerned that it's not. I was just trying to show you that you could verify that. It's just a really ugly function. So there does come a point where it doesn't really, it's not easy to check your answers visually. You just have to trust that you've done the algebra right, done the calculus right. Okay, let's do another one. How about this one? How about y is equal to x squared plus x plus 1 times x to the 5th minus 3x squared minus 4. Find y prime.
Question. Could we simplify this beforehand?
What do you mean simplify?
Well, not simplify. Could we theoretically, now we have a formula to do it differently, but could we multiply all those numbers in and then take our derivative of that resulting number?
Yeah, absolutely, you could. So if we
Okay.
did not have the product rule, right? If we didn't have the product rule, then your only choice would be to distribute, like to expand this, multiply that times that times that, And
Yeah,
this-
expand, not
this-
simplify.
Gross.
this, that's gonna be 9 multiplications that you're gonna have to do, right?
Yeah,
And collect like terms. And then once you do that, you could do them one by one by one by one by one, because the property of derivatives is that if you have addition, subtraction between them, you can do that.
Yeah.
So yes, absolutely, you could do that.
yeah.
Now-
So then the difference between, hey, should I use the product rule or should I just expand it, comes down to, well, which one's going to be harder?
Which one's gonna
Because-
take you more time?
Yeah, because if it was just X times that, it would be way easier to just multiply the X through.
Sure, absolutely. That's why on the review, I gave you one that hopefully is discouraging you from wanting to expand it.
Yeah, no,
Right. This one, you do not, I mean, you could expand this and you get the same answer. It would look totally different, but it would be the same answer. But hopefully you see that there's a product there, right down the middle,
Mhm.
right? There's a product. So that's the way this one's gonna go.
seems like it'll
Okay.
be easier to do it that way.
It'll definitely go quicker, for sure. So there's my product, right? So this entire thing is my first function, and this entire thing is my second function. And so the derivative, the product rule says I should take the derivative of the first one. So let's take the first one here. We need to take its derivative. Multiply that times the second one. Do not take its derivative. See, it feels left out right now. It's like, I want the derivative. And then you're like, okay, well, we'll do that now. Okay, x to the
It's still
fifth.
gonna look ugly.
What's that? It's still ugly?
I mean, if you're to multiply a binomial by a trinomial, it's still.
Well, let's talk about that. Let's get through this and then we'll talk about it. Okay, so here's where we are. Do you all understand the product rule formula being applied there? I've taken no derivatives. I've just applied the formula. I still have to actually do the derivative there and there. Okay, let's do the derivative. So when I take the derivative of this first one here, do you all see that I have addition between these?
Yeah,
So I can do them one by one by one, right? So the derivative of x squared is 2x plus the derivative of 1. I mean, sorry, I just gave it away. Derivative of x is 1, right?
One.
Plus the derivative of 1, which is
0.
0. So that's it. We're done with the derivative of the first one. Now we have to still multiply that times the second one. We haven't done that. We'll just leave it here for now. And now let me go do this operation over here. So I need to take derivative of this. I have subtraction between these. I can do them one by one by one. So we should get 5x to the fourth minus 6x, and that's it. Derivative x to the fifth is 5x to the fourth. Here we have a constant, comes for the ride. The 2 comes out, hits the -3, becomes -6. The power on the square comes down, and I get x to the first power. You see why you have to understand the other rules before we can progress? Like if you're still having trouble with power rule, it's really going to start to hinder you. The other one here, done. Okay, that right there is the raw derivative. Raw derivative right there. Now, could you go and expand this? Could you say, okay, here to here, here to here, here to here, here to here, here to here. Yes, and then here to here, here to here, here to here, here to here, here. Yes, could you do that? Yes. Do we have to? No. Who said we had to? Who says you ever have to expand something? Nobody, right? So we are okay to just leave it here. That is the derivative. All right,
So if we get like on a test, you'd be cool with the answer for this.
that's it. Yeah, that's it. Now later on, we
It's the
will
best solution to that problem.
Yeah, it makes it pretty easy, but now be warned, everyone, that, I mean, we will have to do stuff with this algebraically later. But for now, this is good. This is fine. We're ready to move on and be happy. All right. Okay, we got more to do. We got more to do. How about I give you one, see if you can, is there a question? No? Sure. Okay, how about this one? Y equals the cube root of x cosine x.
I believe there should have been images of the colors.
Wait, what?
Oh,
Was that not meant for us? Okay. Cube root of x cosine x minus square root of x sine x. Find y prime. I give you a minute here. Okay, couple of minutes. I'm going to put up a poll, and the poll, let me see. Yeah, save that. Okay, when you are done, when you think you have an answer, just click one of those. I don't care which choice. I just want to know when someone's done, just click one of them. If you're not done, don't click anything until you're done. I'll put the problem back up here. Hold on. All right, enjoy. All I want is the raw derivative. Don't try and give me some fancy cleaning it up and algebra. Just crank
Wait,
out.
which one's choice 1 and choice 2? What are those?
They're called JC. Okay, junior college.
What's what?
Wait, what is the question? Like,
There is no question. Just click either one of them when you're done.
oh, okay, phew.
Yeah, I don't care which one you click. Just for fun, while you're doing that, I graphed this function so you just see what it looks like. And then once we get an answer, we'll graph its derivative and see if it looks like it's right.
So we don't have to simplify, right? Just the raw derivative.
I think almost everybody, oh no, not everyone's done. Sorry, only 9 out of 25. So we'll just go a few more minutes. All right, I think we've got almost 2/3. Almost 2/3 of you are done. So Jackson, I think you looked like you might have been done first. I couldn't tell. Do you have something?
Yeah, I do.
You want to go for it? You want to tell me what you got?
I guess I got 1/3 x to the negative 2/3, like power negative 2/3 times cosine x plus sine x times the cube root of x, and then all that minus 1/2 x to the negative 1/2 times sine x plus cosine x times root of x.
I'm going to say yes. I just want to clarify on the minus. Did I write this right? Is this the way you want it, or you want me to do something else there?
That's how I have it. Yeah.
Okay.
For the
All right.
second term, wouldn't it be negative sine x?
Yeah, I was gonna say, should that be
Yeah.
minus sine x?
Where, for which one?
The,
Right
yeah,
here?
that right there.
Right there.
That one.
Okay, there might be some little things here. Overall, though, it looks pretty damn close. It's pretty close. Let's go through it and let's work through. Let's see if we can get to this. So the first thing that I noticed is that, well, I have a subtraction, right? So I can do this whole thing by itself and then this whole thing by itself and just work those out, right? So when I take the derivative of this, I'm going to be taking the derivative of all of this and then subtracting the derivative of all of this. Right, that's what I'm going to be doing. There's a property, a rule that allows me to do this. But when I go to take the derivative of this, I see that I have a product. I also have a product right there. So I'm going to have two products I'm going to have to do, but they're separate from one another, right? They live in their own universes here. So in this first one, I apply the product rule. And the product rule says that I will have to take the derivative of the first one, whatever that is, times the second, plus the derivative of the second one, whatever that is, times the first one. And so that right there is just the product rule on this up here, right? That's my product rule being applied. Then I have a minus sign, right? Now, when I'm subtracting everything that this becomes, right? So if this thing turns into being like 2 or 3 or 4 different pieces, I've got to subtract each piece, which means I need to put a parenthesis around this and then do my product rule in here. Does that make sense, everyone? Because you're subtracting the entire expression, whatever it turns into. So when I do product rule here, I have to take the derivative of the square root of x, which I'll do in the next step, times the second one sine x, plus I'll have to take derivative of the sine x, and then times the first one, which is the square root of x. Is everyone on board?
Seems reasonable.
Yeah. So everything I did here is all going to be the derivative of this product here. And now it's time for me to take some derivatives. Now I have a little bit of an issue because it probably would have been better for me to convert these roots over to x to some powers because I want to use the power rule in those. So I'm not ready to take derivative yet. I'm going to turn this into x to the 1/3. I need to take derivative cosine x plus derivative of cosine x, which I'll do on the next line. I'll leave this one as cube root of x because I don't need to take its derivative. Minus parenthesis. Now this one I'm going to write, well, you know, I'm not going to write anything because everyone here, I told you last time, you need to know what the derivative of the square root of x is. So I'm really only changing that first one over. This one right here is the only one. Okay, now it's time for derivatives. So I have derivative of x to the 1/3. The 1/3 comes out. I have x, I subtract 1, I get negative 2/3. Then times the cosine x, I'm not doing anything to that one. And I think this is the part, Jackson, I think you can see it now, what they were talking about. The derivative of cosine, right, is negative sine. So this should give me, I could write plus negative sine. that will turn this into a minus, but I'm just gonna write that. Cube root of x, don't do anything to that. Then I have minus, then in parentheses, I need to take derivative of the square root of x, which is 1 over 2 root x. Now, Jackson, you wrote this, that's perfectly fine with me, okay, because it's the same answer. And then you have sine x, and then plus, now the derivative of sine x, which is cosine x, not negative, right? And then times the square root of x, parenthesis. Yeah, so I'd say the only issues, Jackson, I think you probably learned from that there, and where was the other one? Right there, this, right there. Minor details, but we need to just make sure we're careful, right? Sure. Does everyone understand the use of the parentheses here on this second piece? That it has to be here?
Yeah,
Yeah, because then the whole thing has to be negative. Understand?
Yeah, you're subtracting the whole thing, right? The whole thing, whatever this is, you're subtracting it. So you need to subtract every term. If you don't have a parenthesis here, you're only subtracting the first term. You're not subtracting the second one. All right, that is the raw derivative, and I'm happy with that as an answer at this point.
So I have a quick question for that.
Yeah,
You said for that negative sine x cube root x, you said don't do anything to that. I wrote it as negative cube root x times
Yeah.
sine x. Is that okay?
yeah, you could put that cube root in front. That's what I would do on the next step. I would actually put the square root in front of the cosine. I put the cube root in front of here with a negative. And that would be probably, if I took it one more line, that's what I would do. But this is good. This is what I'm looking for on this test on Tuesday. Like, can you just crank out the derivative? Like, the rest of it's algebra, right? The calculus occurs as you start to use the rules, right? That's what I'm looking for. So I graphed the function, right? I graphed the function. Here it was. Let me take this out of here. This was the function. Pretty cool looking function. And let me type in the derivative. It's going to be ugly, but let me type it in. Where's my derivative? Okay, so it's going to be 1/3 x raised to the negative 2, x raised to the negative 2/3. And then I have times cosine x. And then I have plus sine x times x raised to the 1/3. See if it does it. Yeah, I did that. Okay. Minus parenthesis 1/2. I'll do 0.5 x raised to the 0.5 1/2 again. And then times sine x.
Should it be a minus sine x times x to the 1/3?
Oh, I didn't put, I was looking at the other one. Sorry. Yes, thank you. This is minus. Oh, I forgot. I killed the x on accident there. Okay, negative 0.5, x, and then we have sine x. And then we have plus cosine x times the square root of x. Why is it not doing that? Something's wrong.
You broke it.
I broke it.
The negative on the 0.5.
It didn't like that, did it? What is wrong? It doesn't like this at all. Okay, let me do this. 1/2 x to the 1/2. Something ain't right.
It's negative 1/2 for the exponent.
Oh, negative 1/2. You're right. But that's still not taking it.
think it doesn't like that distributing that negative across all that.
No. Who knows, man? Let me make sure.
Whoa.
Oh God.
Yeah.
Is this what they call like a sinusoid or whatever?
Sinusoidal. Yeah, it is. It is. It's got sines and cosines. I'm not sure why it's not liking me. Oh, you know what? Y equals, there we go. It didn't like it because I didn't put Y equals. Let me just make sure everything else looks okay.
I was gonna say, so you could delete it and type it again. That usually works.
Okay, yeah, this
Good
looks
lord.
good. This looks good. Well, does it? Hold on. That doesn't look good. Something's still off. Cosine X plus, that's supposed to be a minus. This is cube root minus 1/2 X sine plus cosine. See, because we're supposed to, everywhere we see a flat tangent line on the red one, right? Everywhere we see a flat tangent line, we should have an x-intercept on our green one, shouldn't we?
Yeah.
Yeah.
Still not seeing why it's not taking that. This is frustrating. Maybe it's confused by that. There it is. Okay. It was, see, it was trying to put these x's together. It wasn't smart enough to know that. I need to put those arguments in parentheses. Okay, now it works. So everywhere that we have, everywhere on our red graph that we have a flat tangent line, it corresponds to an x-intercept on the green one. And if you look at just maybe one region on the red one where this is increasing, right? We're going up. On the red graph where we're going up, on the green graph, we should be above the x-axis, which we are. Okay.
I have a question.
Yes.
Why is the green line? Why is it? Isn't it supposed to be positive like the red line?
Isn't the? I'm not
Like
sure.
it,
I'm not
it
understanding.
goes down, but the red
Okay.
line goes.
Yeah, so
goes up.
let's look wherever the red graph, let's look at where the red graph goes down, like right in here,
Mhm.
right? The red graph is going down here, which means that the derivative of it, which is the green function, should be below the x-axis. So from here to here, we should expect to see the green graph below the x-axis, which it
But
is.
it also should be negative, right?
It should be what?
It should be negative.
That's what it means to be below the x-axis, right? When you're below the x-axis, your values are negative.
But it's going up there, right?
Where's it going up?
Where the, yeah, right there.
Okay, but you're looking at, see, you're looking at the up and down of the derivative. That's not what we're interested in. The up and down of the red corresponds to the positive or negative of the green. I think you're confusing the two. Positive, a function being positive means it's above the x-axis. A function being negative means it's below the x-axis, right? Positive function is above, negative is below. Increasing and decreasing is a different concept. So where the red function is decreasing corresponds to its derivative being below the x-axis. Where the red function increases, like here, it's going up, 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 up. We should expect to see its derivative up here, positive, above the x-axis. Here it's below. You're not looking at where the derivative is going up and down. You're not looking at that. You're just looking at where it's negative, below x.
I thought they both had to have the same slope.
Nope.
So if the red line is slopes negative, then the green lines also
Nope.
slope is negative.
No, it's not this. The slopes of both of them are not connected. The slope of the red one is connected to the y coordinate of the green one. Not whether or not the green one's going up and down, it's whether or not that y coordinate is above or below the x-axis. So I think there might be a disconnect in that, in your understanding of that.
So they don't have the same slope.
No,
Oh, okay.
I've never said that. I've never said that the function and its derivative have to have the same slope. I've never said that. I've only said that the slope of the original function is equal to the y coordinate or the value of the derivative at the same point. Totally different
Okay.
concepts. Slope and y value, two different concepts.
Okay, thank you.
I would recommend, if you're not making the connection, that you come to my office hours and I try and help you make the connection, because until you see, like, it's like a light bulb. If you don't see the light bulb go off, you're just going to be in the dark with it. It's important that you make the connection. But I mean, sometimes it just takes people a little longer to make the connection. But you're going to have to reach out to me and, you know, come to me for help, and I can do everything, you know, try and explain it in 20 different ways if I can, and we can get it and we can figure it out, but it's going to just take some more time. If I felt like the whole class wasn't getting it, I mean, that's why it's important if you speak up, okay? Because if you don't speak up, I'm just assuming you're getting it. Anyone else? Okay, what time is it? Let me do one that Maddie asked about earlier.
It's gonna be ugly.
I'll keep it clean, but it's, you know, it's an interesting question. So what if we have this? What if we have f of x is x squared times sine x times, I'm trying to make this so you can't get around it any other way. Still limited on the types of functions I have. So okay, I'm going to force you to do it this way. So I think what Maddie was asking, and correct me if I'm wrong here, Maddie, is that does the product rule extend if you have a product of three things? Is that kind of what you're asking?
That's what I was asking.
Okay.
Not just three, but like it continues past.
Like if you had even more, right? 3 or 4
Yeah.
or 5? Yeah. And the answer is yes, we can do this. All right. So does everyone first see that you have a product here and here?
Yes.
Right? You have two products. And our product rule only deals with one product. It does not deal with two products. So watch what I do, okay? Watch what I do. What I'm going to do is I'm going to ignore the second product, okay? I'm just going to ignore it for right now. And I'm going to call this piece my first function. And everything over here, I'm going to call it my second function. And then I'm going to apply the product rule because I have two things being multiplied, right? So the derivative should be the derivative of the first one, right? The derivative of the first one, which I'm going to write as x squared prime, times the second one, right? Sine x times x squared plus x plus 1. Plus what? The derivative of
Yeah, that whole thing in the
second one,
middle
right?
there. Yeah.
The derivative of, so the second one is this, right? That's my second one. And I still need to take its derivative, don't I? And then finish off the product rule times the first one, x squared. So does everyone understand? That's just the product rule applied, treating this as my first one, and this blue one here is my second one. Derivative of the first times the second plus the derivative of the second times the first. Maddie, does that make sense?
Yes.
Okay, I'm going to keep going. This equals, okay, I've got to take the derivative of x squared. That's fine. I can do that, 2x. Then I have sine x. Then I have x squared plus x plus 1, right? Plus, all right, now I've got to take the derivative of this, right? But it's a product, right? So that means I have to do the product rule on this. Y'all see that? I've got to do the product rule on this. So I'm going to just put it all in parentheses so we don't get lost here. I need to do the product rule on this. So that means I need to do the now I've got like a new first and a new second. Do you see that? It's like a new product rule. I've got to do the derivative of the first one times the second plus the derivative of the second one times the first one. Everything I've done there is just this piece. What do I still have slapped onto the outside of this?
Times X.
Times X squared, right? That's this piece. I forgot the derivative sign. Sorry. You'll see right here, I forgot to put the derivative. It was a derivative of the first one times the second, plus I needed the derivative of the second one times the first. And so I've got two more derivatives to go and I'll be done. So 2x sine x times x squared plus x plus 1 plus, I'm going to keep this in parentheses. Derivative of sine x is cosine x times x squared plus x plus 1 plus now the derivative of this piece here, which is 2x plus 1. That's derivative of x squared plus x plus 1, right? 2x, derivative of x is 1, derivative of 1 is 0. And then I still have sine x, but all of that still has an x squared out here. And this is the raw derivative. I have no more derivatives to take, right? Everything I've differentiated, everything has to be there.
Good Lord.
You said this was not bad?
Yeah. Well, I mean,
I could definitely see it being worse.
it's bad, but
Please no.
do you understand the fundamental concept though? You have three things being multiplied, so you treat it like it's two things being multiplied. And then when you do the product rule, you wind up having that one piece in blue, you wind up having it here, and then you have to take its derivative, which means you have a brand new product rule to run on it.
Yeah, no, the concept's not hard. I just see like, you know, messing this up so easily because there's breaking up different parts of it, forgetting to write something or, you know, something like that.
Yeah, definitely.
Yep.
That's one that no matter what, you're gonna want to look back over a couple of times.
Yeah, you just have to be careful. I mean, it's the rules. I've always said the rules are not the hard thing. It's the algebra. The algebra in here is what makes things hard. It's that things get complicated. Parentheses, subtractions. Oh, you forgot this, that. I mean, that's the parts that, I mean, the rule is the rule, right? Derivative first times second plus derivative second times first, done. You know, and that's just a rule. All right, we've got 10 minutes.
Question.
Yes.
Can something like this become infinite?
How do you mean?
Like, can it become like let's say x squared times sine x times x squared plus x1 times x squared times sine x times x squared plus x1, you know, like a loop.
Just like an infinite, you mean like a function that's defined to be like an infinite number of things multiplied together?
Yes.
Absolutely.
Yeah.
And you can either have a sum or a difference. In fact, I mean, we don't have much time left, but in fact, one thing that I'm almost 100% sure I'd be willing to bet a lot of money, a lot of you don't know, because I wouldn't expect that you would know this at this point, is that there are functions like that that you deal with every single day of your life that you were totally unaware of. Like if you take the function sine x, right? If you type, like, go on your calculator, make sure you're in radian mode and type in sine of 2, right? If you type it, I'll do it on mine. Well, no, I won't. You will. You'll do that, okay? It spits out an answer. Did someone do it yet? Radian mode? What do you get as an answer?
Got it. 0.90929. It just keeps going.
0.909 what?
2974268.
And that's where it stopped?
That's the end of what my calculator can do.
That's the end of what the okay, so what did the calculator just do, right? Like what happened? You typed it in, somehow your calculator understands what a sine function is? No, what your calculator did is it plugged that value of 2 into something, but not into a sine function. It has no idea what a sine function is. Here's what it plugged it into. The only thing your calculator knows how to do is add, subtract, multiply, and divide. That's it, right? Those are the basic operations of a calculator. So here's the thing it actually plugged 2 into. X minus x to the third over 3 times 2. I'll put times 1, you don't need it, plus x to the 5th over 5 times 4 times 3 times 2 times 1, minus on the next one, sorry, minus x to the 7th over 7 times 6 times 5 times 4 times 3 times 2 times 1. Has anyone ever seen this? What this thing on the bottom? Do you know what we call these? Anyone ever seen it?
That's a factorial.
The
Hey,
factorial.
Jinx.
Okay, factorial. So this is really like 9 factorial. 9 with the little exclamation point means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's just a shorthand notation. 11 factorial comes next, plus the next one is x to the 13th. Y'all see a pattern? Over 13 factorial minus x to the 15th over 15 factorial. All right. This goes on forever. Okay. It's called an infinite series. It's called an infinite series. And there's a series also for cosine. And for pretty much every function that you'll ever deal with in your life, there's an infinite series that goes with it. You learn this in Cal 2. All right. So when you plug in 2, all you're doing is plugging in 2 here, 2 here, 2 here, 2 here, 2 here. And this is not something we want to do right this minute, but if you get on your calculator and do 2 minus 2 cubed over 3 times 2 times 1 plus 2 to the 5th over 5 times 4 times 3 times 2 times 1, and you start doing that, eventually you'll have to stop, right? You can't go forever, but you stop somewhere, right? I promise you your answer is going to be pretty close to 0.90929. It will be, right? And the further you go, the more precise it gets. So all your calculator has done is basically this and stopped somewhere, right? Now, I'll show you something really awesome. I hope I'm answering your question, Arturo. You can have an infinite series of functions. And so, yeah, this will be pretty awesome. What is the derivative of sine?
Cosine.
Cosine, right? So I'd like for you to take the derivative of this right now. Now, do you see addition and subtractions? Can you take the derivative one by one?
Oh, God.
Oh, it's not bad. It's actually very, very beautiful. Watch. The derivative of this should be what? What's derivative of x?
Just 1.
Yeah.
Okay. Now this right here, this is really 1 over 3 times 2 times 1 times x cubed. That's what that really means, right? It's like this is a number in front of x cubed. So if I take the derivative, what happens? 3 comes out.
3x squared, and then you can multiply it back onto it.
These 3's cancel, and you get a 2 there, right?
Yeah.
So my next term should be minus, because there was a minus there. It should be x squared on top, and then it should be 2 times 1 on the bottom. And then you have the next one. So what happens on the next one? The 5 comes out, and it cancels with that 5, doesn't it? And so you get x to the 4th over 4 factorial. And then on the next one, you get minus, let's see, the 7 comes out, cancels with the 7, and you get x to the 6th over 6 factorial. Next one, x to the 8th over 8 factorial. You seen the pattern? Minus x to
Even numbers.
over 10 factorial. What'd you say?
Sorry, I yawned in the middle of saying it.
Okay.
It's your even numbers.
Even numbers, right?
Yeah, well, sine
These
is
are all
odd.
even powers of x, aren't they?
Mm-hmm.
These are all odd powers of x. Do you remember learning that the sine function is odd?
Yeah.
Yeah, I remember
That
that.
has nothing to do with oddness the way you learned it. It has to do with the fact that its infinite series contains powers of x that are odd only. The cosine function is even because its power series contains only powers of x that are even. If you take a different function like e to the x, it's neither odd nor even. And when you look at its power series, it has both evens and odds mixed in. Okay, so what is my point? I don't know, I'm going off. This is a beautiful fact. We just found the infinite series for cosine. That's what it is. It goes forever. So when you plug that into your calculator, you would get, plug in what's cosine of 2, that's what your calculator does. So Arturo, your question was, can you have this infinite number of functions? The answer is yes. It's actually one of the foundational aspects of computer science, is that when you're trying to solve problems, mathematical problems in computer science, you can only do arithmetic. You can only do plus, minus, multiply, divide. And every power series that you ever have for a function is just simply a bunch of additions, subtractions, multiplications, and divisions. So if every function we ever have can somehow be turned into its power series, then we should be able to differentiate anything, right? Pretty much. Okay, we're way beyond, we're talking Cal 2 stuff right now, but this is like one of the main goals of Cal 2 is to start working with power series. Yeah, I need to shut up. Let's get back to our review. I want to talk about the review.
If
Oh,
this
go
is
ahead.
Cal 2, it won't be on the test, right?
Oh, yeah, we talked about it, so I guess it'll be on the test. No, I'm kidding. We're not gonna. No, if you followed that, great. If you didn't, don't worry about it. And even that one you asked me about with the triple product, right? This, I'm not going to test you on that. Okay, I mean, that might be a bonus. That's bonus material, but it's not testable. I'm not going to test you there. All right. The book does do a triple product though. In the homework, it does. Not in the homework. In the exercise sets, there is a triple product in there. So it's not like completely out of the realm of like possibility. Number 26 in section 2.4, number 26 is a triple product. So they expect that you could do that too, they being the author of the book. All right, as far as the review, I only have about 3 minutes. I sent in the email, I said, don't expect the solutions for this. Now, that doesn't mean I'm not going to provide them. I just don't want you to be sitting there saying, hey, when are you sending out the solution? Sending me an email. Don't expect them. All right, which means you need to, talk with whoever you need to talk to, form study groups, bounce things off each other, see if y'all all agree that this is, looks good. Come to my office hours, reach out to me, whatever. Remember that you have my cell phone number on the syllabus. If you want, you can text me. All right. If you can go if you need to go. I'm just going to talk about this just to be clear on the review. What, how kind of you go about each thing. All these problems that have red on them, you have to imagine this was all before we got the shortcuts, before we got the rules. So I want to make sure that you can still find the equation of a tangent line to a function at a point using the good old fashioned limit. Okay, now I gave you 2 of them just for practice. I don't think I'll give you 2 of them on the test. All right, it's just to give you some variety to practice. Numbers 3 and 4, you're asked to find the derivative at a, and then you're supposed to use the limit definition. Now, intentionally, the second one, I made it a quotient, so we don't have a rule for that yet. So you can't even use the shortcuts on this one because I haven't taught you it yet. So you have to do both of these with the limit. All right, these are so much fun. So I give you the graph of a function, and I want you to graph its derivative on the same page. On this number 5, your graph should be precise. Like you should be able to tell me exactly the values of the derivatives, because each of these line segments is, well, each one of these pieces is straight line, which means you know the slope, which means the derivative when you graph it should be very, very, well, there's no gray area. It is what it is. So that should be a pretty precise picture. And then the next one is the same thing, but now I've got curves in here. And because of that, your sketch is going to be kind of rough, meaning like if it's increasing, right? If the original function's increasing, that means your derivative has to be positive. How far you go up is kind of up to you, all right? So I want to just see how you do with this. This is going to be interesting for sure.
Question.
Yes.
That is a crest?
Cusp.
Cusp. I knew it was something with a C. I was trying to remember just specifically that term.
That is a cusp. All right, on this one, I'm not asking you to graph the derivative. I give you a function and I want you to tell me where it fails to be differentiable. So tell me where the derivative does not exist and to explain why the derivative doesn't exist at the points you say it doesn't exist. So if you say, oh, the derivative doesn't exist at 4, at x equals 4, I'm not even looking at the graph. You say, oh, the derivative doesn't exist at x equals 4. I want you to say why. Because blah, blah, blah. All right. And then we start with the derivative. So from this point on, if I ask you for a derivative, you can use the rules. All right. So this first one, look what I'm asking. I give you a function. I'm asking you for the third derivative at -1. That means you have to take derivative of this 3 times. And then once you get that answer, plug -1 into it and it'll spit out something, right?
So if we're ever, so just real quick, if we're ever asked to do this and it has like a, instead of an X, it has like a number in there, that just means after you do whatever derivatives, you just plug it into it.
That's right. After you actually execute the 3 derivatives, boom, 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 then you replace the X in that third answer, you replace it with whatever's in there, -1 here. On this one, I give you a function, it's got a, minus, plus, plus. So you can do these individually, right? Just like this one. And then you're gonna have to find the second derivative. This is really me just like torturing you to make sure you understand the power rule. That's really what this is about. Okay, if you can do these, power rule should be no problem for you. Number 10 is very similar to a problem from the book.
Yeah, I remember that one. It was Trixie.
Yeah, so you just have to do some algebra before you actually do this derivative.
That one in particular was why I asked you about the multiplying it out versus using the power rule.
Yeah.
Because I remembered seeing that one.
Mm-hmm. All right, number 11. So here, again, this is similar to a problem that was in the homework. I give you a function, here it is. I ask you to find where this function has horizontal tangents. What does that mean? Where the what? Horizontal tangent, where the what? I'm asking you where the what then?
Tangent, a regular line, like a perpendicular or something?
Would it be where the slope of the tangent is 0?
So I want to know where the tangent line is horizontal, right? Which means that it's flat like this, and horizontal lines have a slope of 0, right?
That'd be at the x-intercepts, right?
The x-intercepts of the derivative, right? So basically, you're supposed to take the derivative and set it equal to 0, right?
Oh.
The derivative represents the slope of the tangent line. That's what it represents, right? The slope of the tangent line. So if I'm asking you where the slope of the tangent line is horizontal, I'm asking you where is the derivative 0? So just simply take the derivative of this function, set it equal to 0 and solve. 12 is the same thing, but it's harder. But there was a problem like this in your homework also, because you have to solve a trig equation, and there's an infinite number of solutions to this. This goes back to pre-cal. This goes back to pre-cal. And let's see, this one, find the equation of the tangent line and the normal line. So I give you a function, I give you a point, you find the equation of those 2 lines. So we talked about at the beginning of class what a tangent and normal are. Find the 137th derivative of cosine. So that's where you're going to probably have to make a table, like figure out what the pattern is, do your mod. The hint I'll give you is the same cycle. It cycles every 4, so you're going to do mod 4 on it. You just have to figure out what mod gives you what. So if you do mod and get 0, what answer do you get? If you do mod and get 1, what answer do you get? Let me see. Ooh, okay. Why did I give you number 16? Scratch 16. We did not do the quotient rule. We have not done this. We don't know how to do quotients yet. Actually, you can scratch that one and this one. So 16 and 18, take off the table here. 17 is like the one I did in class earlier where we were talking about, do you multiply that all out or do you do the product rule? It's up to you. I recommend that you treat this like a product and do your product rule. Treat that like your first one and second one and then just crank it out. Give me the raw derivative. All right, the last one here Yeah, the last one, the position of a particle at time t is given by a function. So I give you a function that gives you position, and then I ask you for the acceleration at a certain point in time. So you just have to remember what I told you about this, right? You start with position. The first derivative gives you what?
Instantaneous moment of time or some shit.
Velocity.
Instantaneous velocity. And the
Velocity.
second should give you acceleration.
Second derivative is acceleration. So basically all I'm asking you to do there is take the derivative twice and plug in 4. That's it.
It's harder because it's a word problem.
Well, it seems harder, but you asked for the acceleration at a particular point in time. So you just take the position function, differentiate twice, plug 4 in, and your answer will be, well, go back and look in your notes. We
Yeah.
talked about the answer for acceleration. So
Dude, it's kind of ridiculous how that goes. Like I had some homework in physics the other day, and it's like beginner physics. It's the one that I didn't technically have to take. I looked at it and said it would be nice to get some refresher on this because it's been a while since high school, and I'm sitting there doing problems, and they're way easier than this stuff. But it's all word problems, and so it's just tripping me up super hard.
yeah, getting from the word problems to the math.
Yeah,
is always the
it's
challenge.
that transition of here's a bunch of values and figure out what they all mean. Have fun. Versus, yeah, formula numbers. Do it.
Yeah. All right. Are there any questions? We're over on time here. So is there anything else I can address?
Yes, sir.
Yes, sir.
Could you please post the notes from today and all the way back to the 14th?
I have done that. I sent an email about it. Did y'all get that? That instead of posting them in Canvas, I'm sharing them in a folder.
Yes, sir. And it only shows the 9th.
Really? Let me see. I'm trying. This is something new. So let me just go to my folder so you can see what I see. So I go to here. I've got fall 2413 Zoom notes. See, it says it's shared here. And I have all of them here. And it says they're all shared. Are you not seeing? You're not seeing any of these?
From the last email that you sent, it only shows September 9th.
Really? I can't believe you've been patient enough to not say anything already. I've been diligent about it. I'm like, I'm getting them in there, and after every class I post them. Let me see. Let me see the link I sent you to see what it does for me. So, do you happen to have the date that I sent that?
The email has it. When I click on the link in it right now, it pulls up all of them.
It does?
All the way up to yeah. So like
maybe refresh your browser. I don't know.
I only have it up to the 9th as well.
So I went to my inbox and I have that email from you from the 18th.
It's the 18th.
And
okay, there it is.
I clicked on the link. Oh, now it says the link has been removed. I don't know what that's about.
What?
Yeah, I can't open it either.
Oh, I see what it is. It's not in order.
Oh,
yeah, it orders it its own way. I hate the way it orders it. I don't know why it orders it this way. Are they all there?
Yeah.
They are all there? Okay.
I see it now. Yeah, it's all there. It's tab order.
Yeah.
Computers don't know what to do with dashes.
Yeah, if you try and sort it, yeah, so. Yeah, see, it treats it, we call this dictionary order. So it goes 9, and then it looks at the 2, and so 2 comes before 7, right? And then the 8. Do you see what I'm saying? Like that's actually called dictionary order, and for some reason that's the way it sorts it. I can try and change that the way I name it, but are we good, Daniel? They're all there. They should all be there.
Yes, sir. Just not for today, though.
Just not for today.
Yes, sir.
Yep. So I will have that there in like 10 seconds.
Thank you.
Should be there now.
I have a question. What's our homework?
Oh yeah, homework. I would say if you're going to do anything out of 2-4, because we have not done all product rule. I mean, sorry, we have not done the quotient rule. I would say from this to stay 3 through, you got to stay just in the beginning, probably, I would say do 3 through 10. That's about it. Everything else is quotient rule pretty much. So I would just do, yeah, don't do any of this right now. Just do 3 through 10. If you want some practice for today.
3 through 10, okay.
Yeah, 3 through 10. Those are the only ones that are products.
This is for 2.4.
2.4, yeah.
Oh, okay.
That'll give you some practice. That'll give you some practice for the product rule, but really look at the review is really the biggest thing for you to make sure you can handle the review.
Yeah, fine.
Yeah. I made it long. It's kind of long. The review is kind of long because I wanted to give you like things to practice. There's no way I think I can make the test that long. So just keep that in mind. I may not test you on every single topic there, but if you can handle the review, you should be okay.
We gonna have another bonus question on the exam?
Maybe.
Cool.
Yeah.
That was, it's real nice having a potential grade of 110.
Yeah.
Yeah, it really saves like that one little like problem you might fuck up on or something.
Yeah.
Okay, I do have one question.
Mm-hmm.
Okay, so you said our exam is on Tuesday, correct?
Yes.
So on the review, we have some problems. I think specifically it was problem number 10 that we looked at. I know we haven't gone over quotient rule yet. If that's something that we're comfortable with using, will we be allowed to use that on the test, or do we have to do it without quotient rule?
You mean if you do this one with quotient rule?
Yeah, like that, for
Do
example.
you know the quotient rule? Is that what you're saying?
Well, I've taken Cal 1 before.
Yeah,
so
I'm just saying, that's what you're saying. If you know the quotient rule and you take the derivative of this with the quotient rule, will it be wrong? I'm okay with that.
Okay.
I'm okay with that. Yeah, I mean, it's still right. It's still the derivative. Just make sure you do the quotient rule right.
Gotcha.
Yeah. But just from the perspective of just being like a calculus student, quotient rule is more trouble than I think it's worth here, because you can just do x cubed over x squared, x over x squared, root x over x squared, 1 over x squared. You just get 4 terms, all power rule, boom, you're done. Like split it into 4 terms, power rule on each one, you're finished. Quotient rule, you're going to be doing derivative at the top times the bottom minus derivative at the bottom times the top over the bottom squared. It's going to get messy. You're going to wind up doing derivatives multiple times. So yes, it'd be fine with me, but it would just be, I think, more work than it needs to be.
Oh no, I hadn't actually, like, I was having trouble thinking of another way to do that, which is why I was just kind of like, well, the first thing my brain goes to is quotient rule. So I was like, would I be allowed to use that just in case I get stuck on a problem and I can't think of another way to do it?
Yeah, no, I understand. That'd be fine.
Wouldn't that be?
Can we also? Oh, sorry. Go ahead.
Oh, I was just gonna say, wouldn't that just be effectively subtracting that exponent from the other x's?
Yeah, for all of these, just 3 minus 2, 1 minus 2.
Yeah, no,
half
one, and
minus
then like 3
negative
halves,
2.
negative something.
Yeah. What were you say, Ethan?
I was saying, couldn't you take the x squared, bring it up,
-2,
and then like do some algebra, multiply it out, and then take the derivative from that?
the same thing. You get the same.
I was doing some of that in the homework. I didn't know if it was correct.
You're saying bring that x to the 2 on the bottom as an x to the -2.
Yeah.
Yeah, that has the exact same effect.
Has the same, it does the exact same thing. But either way, so it, with algebra, sometimes there's just like kind of different ways that you can get to the same result, just depending on the path. As long as you don't break any rules, you're good. It's when you start to do stuff you're not allowed to do is when things start to fall apart. So that's completely legal, and I don't think it's any faster or slower. I think it's more of a personal preference, really. So if you like that, bring the x up as a -2, distribute, go for it. All right. How about this? I had some students asking me, like, generally the earlier, just about like, how do you when you go back and you think about solving a trig equation, because that's really what that problem is about. If you're back in pre-cal and you're asked to find, let's say, when is sine of x equal to, let's say, √3/2. Like, let's say you're working a problem, you finally get to this final result and you want the solutions to that equation. There's a lot of things you need to understand to answer that. Because first, I'm not telling you, or nobody's telling you, that x is restricted between 0 and 2 pi or anything. There's an infinite number of answers for this equation. So the way that I look at it is, I go back to the unit circle and I think about what the sine function is. The sine function corresponds to the y coordinate of the point on the unit circle. So I'm asking myself, where on this unit circle, where is the y coordinate equal to √3/2? And so you have to know the unit circle to answer this. You have to know it happens here at this angle, because that is the point 1/2 √3/2. And so the y coordinate is √3/2. That's the angle pi/3. But it also happens right here, because that's -1/2 √3/2. So this also has a y coordinate of √3/2. So there's two places, right? And that angle is, what is that angle?
2 pi/3.
2. So yeah,
Yeah, that's right. 2 pi/3.
Yeah, so yeah, it depends on how, yeah, we'll do that one. 2 pi/3. Okay. You have to know that. You have to know that. Now, that means you might have a, unit circle that you've learned, or however you've learned it. This is pre-cal topic. So two answers, right, are pi/3 and 2 pi/3. Those are two answers, but it's not all of them. So I know in my pre-cal class, what I teach them is, okay, how do you get to this angle? Well, you can start at pi/3, right? But then you could, if you want, spin all the way back around once, or you could go around twice, or you could go around 3 times, or 4 times, or 5 times. So that means that the angle here, x, would have to be pi/3 plus any number of full rotations you want. So
In 2 pi?
N2 pi or 2 pi n represents all the possible full rotations, both clockwise and counterclockwise, because this n represents an integer. So n represents either 0, 1, -1, 2, -2, 3, -3, 4. So it's all possible integers. So if you use 0, then it's just pi/3. If you use 1, then you're going to pi/3 and adding a full rotation. If you do n is 2, then you're starting at pi/3 and adding 2 full rotations, and then backwards too. That's only half the answers, though, right? The other half come from the 2 pi/3. So you can make the same argument. Start out at 2 pi/3, and then do full rotations to get back. So 2 pi/3 plus 2 pi n. Those are all the solutions to that equation. So when you get to that problem here, when this says, if this function, if the original function is x minus 2 cosine x, right? X minus 2 cosine x. X minus 2 cos x. Here's the graph of that function. We are asking, where does this have horizontal tangents? Where, right? Where are the tangent lines horizontal? So we go to the picture. Well, shit, there's an infinite number of answers, right? I'm not asking for just two of them. I'm asking for all of them. So the way you're going to do it is you're going to take the derivative, right? Set it equal to 0. And when you do that, you should get a trig equation similar to the one I just showed you. And so your answer should be some sort of general solutions like this. And that's your answer. So you should have an n in there in your answers. Hope that makes sense. If not, you still have till Tuesday to figure it out. All right, we
Yeah, so
good?
screwed.
You're fine. You're fine. Just come for help if you need it. Text me or something. You know, hit each other up, do a study group, you know, help each other out. We used to, I know when I was a student, we used to divide and conquer, you know, we would be like, okay, I'll do the odds, you do the evens, you know, and then we'll get together and we'll study and we'll help each other out. You know, I don't know, do what you got to do, but I know there's not really a big platform for you to be able to meet like in person, to, you know, but you've got Zoom, you got ways to communicate with each other. So I know some of y'all study, no? Any of y'all study together? A couple of you? All right, it's 3. I got to run.
All right. Have a nice day, sir.
Yep.
Thank you.
Appreciate it, sir.
Don't hesitate to reach out.
Of course.